Hi everybody, and welcome to exercise 5 on page 83. Let's take a minute to read this together. So consider the matrix given to the right, and that's this matrix A. And in part A, they ask us, is the set beta 1, consisting of the three vectors that you see, a basis for the null space of L of A? Okay, the left multiplication operator. All right, well, there are a number of ways that we could answer this question. Our strategy in this case is going to be kind of systematic. So what would it take to be a basis here? Well, the first thing that we need to check is, are these three vectors even in the null space? Okay, to have any chance to be a basis, we need those to be vectors in the null space. So how about if we start out by doing that? Okay, so I'm going to give these vectors names. Okay, actually, just to avoid some writing here, let's label them. We'll call them U1, U2, and U3. Okay, and if we do that, I'm going to let you check this part. This is really just doing matrix multiplication. So we'll say it this way. Since A times U1 and A times U2 and A times U3, you can do those three matrix multiplications, all give us the zero vector. We know, by definition, that those three vectors are in the null space. Okay, or another way of saying that is that this set beta 1 is a subspace of the null space. Okay, so at least we have that. Okay, now, one other thing that has to be true if we want to have any chance for beta 1 to be a basis is that this has to be a linearly independent set. Okay, so let's check that. So the calculation to check for linear independence, we're going to form a matrix that has those three vectors as its columns. Okay, and let's see, we've got quite a few coordinates here. Okay, so there's U1, and then U2 looks like 0, 2, 1, 1, 0. Okay, and then 3, 2, 2, 1, negative 1. Okay, let me make sure that I wrote all of that down right. Okay, looks good. And we're going to do row operations on this, and if you do that, here's what you should end up with. Okay, 3, negative 4, 1, 0, 0. Okay, and notice where we wind up with pivot positions, here, here, and here. And the key is that we get pivot positions in every column. Okay, so in this particular system that we wrote down here, there are no free variables. Okay, and that tells us that these vectors are indeed linearly independent. So this calculation verifies that beta 1 is linearly independent. Okay, so far so good. We've got a linearly independent set of vectors that are in the null space. Okay, now to show that this is a basis, we need to do one more thing. We could try to show that these vectors span the null space. That would be difficult to do directly, so what we're going to do is to use a theorem that we had earlier in the course. Okay, if we knew what the dimension of the null space was, then, and the dimension turns out to be 3, then we would know that because we have 3 linearly independent vectors, it has to be a basis. That's going to be our strategy. So how do we find the dimension of the null space? Well, the key is to look back up at the top of the page of this matrix A. Okay, notice that it's already in echelon form, which is convenient, and so we can pick out the pivot positions. And how many free variables are there in this system? If you think of AX equals 0, we've got 2 pivot positions. That means there are 3 free variables. And that tells us from our previous work that the dimension of the null space matches 3, the number of free variables. Okay, so let's say it this way. Okay, so since A is in echelon form, okay, we can see that the system AX equals 0 has 3 free variables. Okay, we notice that by noticing that we have 2 pivot positions. And that tells us that the dimension of the null space of L of A equals 3. Okay, so again, just to recap, 3 linearly independent vectors in the null space, that's what beta 1 is, and so since the dimension is 3, we know that beta 1 is a basis. Okay, that was DF4, dimension fact 4. Okay, you can find that on your theorem sheet. Beta 1 is a basis. Okay, good. So we've answered the question and explained why that's true. Let's move on to part B. It's asking us a similar question. Now they give us a second set. Is beta 2 equal the set of those 3 vectors a basis for the null space of L of A? Okay, and again, justify our answer. Okay, and in this case, I claim that it's not a basis. Okay, I'm going to see if I can convince you of this. So you might look at that and say, well, 3 vectors again, seems like maybe we have a basis. But turns out that even though beta 2 is also a subspace, or I'm sorry, a subset of the null space of L of A, you can check that by taking A and multiplying by each of those 3 vectors, and you'll see that you get 0. And beta 2 contains 3 vectors. It's actually not a basis. Okay, so what's wrong? It's got the right number of vectors, and it's a subspace of the null space. Well, the problem turns out to be linear independence. Okay, so to see this, observe that. All right, so to check linear independence again, we're gonna form a matrix with our vectors being the columns here. 1, 1, 1, 0. Okay, and then 0, 1, -3, -1, and 2. Okay, let me just make sure I wrote that down right. Okay, it looks good. And turns out if you do row reduction in this case, here's what you end up with. 1, 0, 0, 0, 0, -2, 1, 0, 0, 0, and then finally, 0, 1, 0, 0, 0. Okay, where are the pivot positions? There and there. And the problem is there's no pivot position in the third column, meaning that this system that we're looking at here has a free variable. And if we've got a free variable, there are going to be non-trivial solutions to the relevant system. Okay, that means that we can't have linear independence. All right, so we can summarize that by saying the following. Okay, since there's no pivot, third column directly above, okay, the vectors in beta 2 are linearly dependent. Okay, and that's the problem. So beta 2 can't be a basis, even though everything else looks good. Beta 2 is a subset of the null space, and it contains 3 vectors. The fact that it's linearly dependent prevents it from being a basis.